Welcome back to the second module of Well Testing and Analysis 2. In the first module, we focused extensively on fractured reservoirs, flow behavior, fracture detection, and conventional evaluation methods, including an introduction to type curves. We also explored some fundamental theory that underpins advanced testing methods. In this second module, our journey will move into more specialized well testing methods and interpretations, particularly focusing on injection well testing, drill stem testing, interference, and post-testing, as well as gas well testing and type curve matching in more detail. We will also cover elementary horizontal well testing and analysis, which is becoming increasingly important in today's oil and gas industry where unconventional resources play a significant role. This module will not only provide technical details but will also help you understand practical applications, the kind of knowledge you will need in real-world well test planning, execution, and interpretation. Section 1. Injection well testing. Injection wells play a vital role in many petroleum production systems, particularly in secondary and tertiary recovery operations. When a reservoir's natural drive is insufficient to produce at economic rates, we often introduce injection schemes, water flooding, gas injection, CO2 injection, or even steam injection in heavy oil cases. Injection well testing involves evaluating the injectivity and capacity of a well to accept fluids at desired rates and pressures without causing formation damage or fracturing the formation unintentionally. 1.1 Fall-off analysis. Let's begin with the fall-off test, one of the most common and effective injection well tests. A fall-off test is performed after an injection period when the well is shut in. The pressure decline is recorded over time, and from this data, we can extract valuable information about reservoir transmissibility, skin factor, and reservoir boundaries. The principle is similar to a build-up test in a production well, except here the preceding period involves injection rather than production. Procedure. Inject fluid at a constant rate for a sufficient period to achieve pseudo-steady state. Shut in the well abruptly and begin recording pressure versus time. Continue recording until sufficient late-time data is collected for analysis. Interpretation. Early-time data reveals wellbore storage and skin effects. Middle-time data reflects radial flow in the reservoir. Late-time data can indicate boundaries or heterogeneities. Practical challenges. Temperature effects. Injection fluids often differ in temperature from the reservoir, which can distort pressure readings. Multiphase flow. If injected gas is dissolving into oil or water, additional complexities arise. Non-Newtonian injected fluids. In polymer flooding, viscosity behavior may not follow standard Darcy assumptions. 1.2 Injectivity test. An injectivity test measures how much fluid a well can take in at a given pressure. Procedure. Start injection at a low, steady rate. Gradually increase the rate while measuring the corresponding bottom-hole pressure. Plot rate versus pressure. Applications. Determining fracture pressure. Estimating permeability and skin in injection mode. Establishing operational injection limits. If plotted, a linear relationship between rate and pressure suggests Darcy flow, while deviations can indicate near wellbore restrictions, partial plugging, or fracturing. 1.3 Step rate test. A step rate test is a specific injectivity test designed to determine fracture initiation pressure. Procedure. Inject at a low rate for a fixed period, often 30 minutes to 1 hour. Record stabilized injection pressure. Increase injection rate by a fixed step and repeat until a sudden decrease in slope is observed in the rate pressure plot. The point at which slope changes marks fracture initiation. Why it matters. Preventing unintended fracturing during water flooding. Designing hydraulic fracturing treatments by knowing the formation breakdown pressure. Section 2. Testing methods. 2.1 Drill stem testing, DST. DST is a classic but still valuable technique, particularly in exploration wells. It allows for temporary completion of a well to test its productivity without full production infrastructure. DST tools isolate a section of the formation and allow controlled flow to the surface while measuring pressure and temperature downhole. Advantages. Direct measurement of formation pressure. Early assessment of reservoir productivity. Fluid sampling for PVT analysis. Limitations. Operational risks. Well control must be carefully managed. Only gives short-term production potential, not long-term deliverability. 2.2 Interference testing. An interference test involves two or more wells. One well is produced or injected while pressures are recorded in nearby observation wells. Purpose: determine reservoir continuity between wells. Measure average permeability over larger distances than single well tests. Identify barriers, sealing faults, or high permeability channels. 2.3 Post-testing. Post-testing is similar to interference testing but uses short-duration pressure pulses rather than long production or injection periods. Advantages: less disruptive to production. Can detect connectivity over large distances. Typical application: used in offshore environments where well testing can be costly and operationally disruptive. 2.4 SFT Selective Formation Testing. An SFT tool allows selective testing of specific intervals in an open or cased hole. This is especially useful in multi-layered reservoirs, allowing each layer's pressure and fluid characteristics to be measured independently. Section 3. Gas well testing. Gas well testing requires some special considerations because gas compressibility, high mobility, and nonlinear flow behavior change the interpretation of pressure transient data. Key differences from oil well testing. Real gas properties must be used. Gas deviation factor, Z. Pseudo-pressure and pseudo-time transformations are often applied. Early time data is more sensitive to skin and wellbore effect due to higher velocities. Practical challenges. Multi-rate testing often required to detect turbulence effects. High-velocity flow may induce non-Darcy effects. Section 4. Further type curve matching. Type curves are a graphical method for interpreting pressure transient data by matching measured data to theoretical solutions. In Module 1, we introduce type curves. In Module 2, we go deeper by including composite reservoirs with different permeability zones, considering fractured well models, addressing horizontal wells and multilateral completions. Type curve matching is both an art and a science. A skilled analyst uses curves as a guide but cross-checks results with independent reservoir data. Section 5. Elementary horizontal well testing and analysis. Horizontal wells are increasingly common because they expose more reservoir contact and can drastically improve productivity. Unique flow regimes. Early linear flow along the wellbore. Transition to radial flow. Sometimes, late-time boundary-dominated flow appears sooner. Challenges in testing. Pressure response can be dominated by near-wellbore effects for a longer time. Heterogeneous reservoirs may behave differently along the lateral length. Applications. Estimating effective drainage area. Optimizing completion intervals. Diagnosing production issues such as heel-toe effect. In this module, we explored injection well testing, specialized testing methods, gas well testing, advanced type curve matching, and the basics of horizontal well analysis. Each of these techniques plays a vital role in modern petroleum engineering, and their mastery allows engineers to better understand reservoirs, optimize production, and enhance recovery strategies.